Hi, my name is Aven Satre-Meloy, and I'm a research scientist at Lawrence Berkeley Lab. Together with my colleagues and our partners at the Brattle Group, we've developed scenarios that explore the future of U.S. building energy use and CO2 emissions through mid-century. The U.S. has embarked on an incredibly ambitious journey to mitigate climate change. This journey is guided by three overarching goals set forth by the Biden administration, shown here. Our research work aims to support these ambitious goals by asking a simple yet essential question about the pathways to achieving them. What is the role for buildings? Historically, much of the work on energy system decarbonization pathways has focused on supply-side energy generation technologies and CO2 removal solutions rather than demand-side approaches in buildings. But buildings should be a central focus of energy system decarbonization. They account for around 35% of current U.S. greenhouse gas emissions and nearly 75% of U.S. electricity consumption. Understanding the technologies and policies that are needed to decarbonize the built environment, as well as highlighting how buildings can facilitate decarbonization more broadly in the U.S. energy system, is critical. Our team of researchers sought to answer this question with unprecedented detail and granularity. We developed 12 scenarios that represent variations in technology and policy drivers to decarbonize buildings. We use a modeling framework called SCOUT, which is developed for the U.S. Department of Energy to conduct our demand-side scenario analysis. Our representation of building technologies is comprehensive, covering over 150 residential and commercial building decarbonization measures, including both existing market-available technologies as well as next-generation innovations that will enter the market in the next decades. Our partner Brattle conducted granular power system modeling for 25 U.S. grid regions using its GridSim model to understand the electricity generation mix and infrastructure costs for a range of supply-side grid scenarios, including a scenario representing the Biden administration's zero carbon by 2035 goal. Our analysis couples these demand and supply-side models to assess the impacts of demand-side building measures at an hourly temporal resolution through 2050. On the next several slides, I will highlight the three key findings of our work that I hope you will take away from this presentation. First, we find that deep reductions in building sector CO2 emissions are achievable by 2050. Our most aggressive scenario finds that building sector emissions can be reduced up to 91% below 2005 levels by 2050. These figures show the range of scenario results for building energy-related CO2 emissions and building site energy and electricity use. As mentioned, we represent 12 scenarios, including 3 benchmarks for low, moderate, and aggressive decarbonization of the building sector. While all of these scenarios represent reductions in building site energy and CO2 emissions below a reference case, we find that building electricity use in some scenarios grows rapidly. These high electricity scenarios envision a building sector that electrifies but does not prioritize energy efficiency. We include these to explore important dynamics between different types of building decarbonization measures and their interaction with the power system. This is explored further in our second finding. Building efficiency and electrification are critical for the most aggressive pathways. Our results show that building measures account for nearly half of total sectoral CO2 emissions reductions by 2050. Emissions reductions attributable to building measures are shown here in these figures by the affected end use in the colored wedges. The remaining reductions are attributable to power system decarbonization, which is shown as the dark gray wedge in the figures. While this may seem like an expected finding, it is an important component of our work. Most pathway studies simply assume buildings will electrify and that as the grid decarbonizes in parallel, the building sector will effectively be decarbonized. While this is true, it's also an oversimplification. Our work yields a much more nuanced attribution of demand versus supply-side technology change, highlighting the essential roles of building efficiency, electrification, and flexibility. Because without strong support for building measures, decarbonizing the power system becomes a lot more challenging and costly. This leads me to our third and most important finding. We find that aggressive building efficiency and flexibility substantially reduce the cost of grid decarbonization. Building measures could avoid over $100 billion in bulk power system investments each year by 2050. Our results show how these savings are attributable to different building end uses and also different measures and customer types. You see that power system cost savings grow considerably from 2030 to 2050 as building technologies are deployed more widely across the building stock. These avoided cost savings represent up to 35% of the incremental cost of transforming our power system to be fully zero carbon by 2035. In summary, building efficiency and flexibility are critical decarbonization tools to pair with building electrification. And they won't just yield deep reductions in building sector emissions. They're also essential for limiting the costs of decarbonizing the US power system. This was a lightning talk, so it excluded most of the technical detail and methodological assumptions of our work. But if you're interested, you can find detailed methodology, a suite of interactive visualizations, and a link to download our full study at buildings2050.lbl.gov. Thank you.